Measurement changes things, not in the way that a thermometer slightly warms the liquid it touches, or the way that observing an animal in the wild alters its behavior. The change is more fundamental than that. In quantum mechanics, the act of measurement does not just disturb a pre-existing property. It appears to bring the property into existence in the first place. Before the measurement, the property was not hiding somewhere waiting to be found. According to the most successful theoretical framework in the history of science, it simply was not defined. This is not a philosophical speculation or an open debate among fringe theorists. It is the operational conclusion of the most precisely tested theory humanity has ever developed. Quantum mechanics predicts experimental outcomes to more decimal places of accuracy than any other framework in physics. Better than general relativity, better than any classical theory, better than any rival model proposed since 1925, and built into its mathematical structure at the deepest level is the implication that physical properties do not always have definite values until a measurement forces them to take one. The instinct to push back against this is understandable. Everything about ordinary experience suggests the opposite. A ball sitting on a table has a definite position. A cup of water has a definite temperature. The moon has a definite location, regardless of whether anyone is looking. The idea that a particle might not have a definite spin, or a definite momentum, or a definite energy until something interacts with it seems to belong in philosophy. Not physics, but the data does not care about the instinct. Experiment after experiment for 100 years has returned results consistent with the quantum description and inconsistent with any classical alternative that assumes definite pre-existing properties. The universe, probed carefully enough, does not behave like a collection of objects with hidden values that we simply have not measured yet. It behaves like a system whose values are genuinely undetermined until the interaction that determines them occurs. Understanding why this is true, what it implies, and where the frontier of the research now stands requires going back to what quantum mechanics actually says. Not the popular version filled with metaphors about cats in boxes, but the actual structure of the theory and the specific places where it forces a rearrangement of our assumptions about reality. The foundation is the wave function. Every quantum system, an electron, a photon, an atom, or any composite object that has been properly isolated from its environment is described not by a list of definite properties, but by a mathematical object called the wave function. The wave function encodes probabilities. It tells you, for any possible outcome of any possible measurement, how likely that outcome is. It does not tell you what the outcome will be. It tells you the full probability distribution over all possible outcomes when a measurement is performed. The wave function appears to change discontinuously. Before the measurement, it describes a spread of possible outcomes. After the measurement, it describes a system with a definite value for the measured property. This change is called wave function collapse, and it is one of the most contested aspects of the theory. Not because there is any doubt about the predictions it generates, but because the mechanism of the collapse is not explained by the Schrödinger equation itself. The Schrödinger equation, which governs how quantum systems evolve over time when they are not being measured, is a smooth, continuous, deterministic equation. It does not produce sudden jumps. It does not produce collapses. It evolves the wave function from one smooth spread of probabilities to another smooth spread of probabilities, continuously and predictably. But actual experimental results are not smooth and continuous. They are sharp and definite. When you measure the spin of an electron, you get a single answer. You do not get a smear of fractional spin values. The mismatch between these two descriptions, the continuous evolution of the Schrödinger equation and the sudden definite outcomes of Measurement is called the measurement problem. It is arguably the deepest unsolved conceptual problem in physics. It has been with the theory since the beginning, and 100 years of experimental confirmation have not resolved it. They have only sharpened it. What the experimental confirmation has done is eliminate one class of possible solutions. For several decades after quantum mechanics was formulated, a natural escape route seemed available. Perhaps, the argument went, the wave function simply reflects our ignorance. Perhaps the particle really does have a definite spin before measurement. We just do not know what it is. The wave function would then be like a probability distribution in classical statistical mechanics, a tool for handling uncertainty about a system whose underlying state is perfectly definite, just unknown to us. This interpretation is called a hidden variable theory. The idea is that quantum mechanics is incomplete, that behind the apparent randomness and indeterminacy, there are hidden variables that determine the outcomes in advance. If we could access those hidden variables, the probabilistic character of quantum mechanics would dissolve and we would recover determinism. The physicist John Bell closed this escape route in Bell derived a mathematical inequality, a constraint on the correlations between measurement outcomes that any hidden variable theory must satisfy if those hidden variables obey certain conditions. Specifically, the conditions were locality. The hidden variables associated with one particle cannot be instantaneously influenced by what happens to a distant particle, and realism. The assumption that particles have definite values for their properties before measurement. Bell's inequality says that any theory satisfying both locality and realism predicts that certain correlations between the measurement results on pairs of entangled particles must fall below a specific numerical threshold. Quantum mechanics predicts correlations that exceed that threshold. The experiments to test this have been performed repeatedly, with increasing rigor and decreasing loopholes since the 1970s. Ailing aspects experiments in 1982 were landmark tests that confirmed quantum mechanical predictions. John Clauser Ailing aspect and Anton Zeilinger shared the Nobel Prize in Physics in 2022, specifically for experimental work that has demonstrated violations of Bell inequalities. The results are unambiguous. The correlations between entangled particles exceed what any local hidden variable theory can produce. The violations are not marginal. They are large, consistent, and reproducible. This means one of Bell's two assumptions must be false. Either locality fails, events at one location can be influenced instantaneously by distant events, or realism fails. Particles do not have definite values for properties before they are measured. Most interpretations of quantum mechanics abandon realism in at least some form. The particles genuinely do not have definite spin values, definite positions, or definite energies until the appropriate measurement is made. The implications of this, for the classical picture of the world, are severe. If particles do not have definite properties before measurement, then the everyday world, which is composed of particles, rests on something far less solid than it appears. The definiteness of the macroscopic world is not a reflection of some underlying definiteness at the quantum level. It is an emergent phenomenon, arising from the way quantum systems interact with each other and with their environments at the scales we are accustomed to. The process that produces this emergence has a name. When a quantum system, say a single particle with an indefinite spin, interacts with its environment, the quantum correlations that give rise to indefiniteness do not disappear. They spread. The particle becomes entangled with the molecules of air around it, with the photons that strike it, with the atoms of any surface it contacts. As the entanglement spreads to more and more particles, the original quantum superposition becomes effectively invisible to any local measurement. The system behaves as if it had a definite classical state, not because the quantum description has been replaced, but because the decoherence has made the interference between different quantum outcomes unmeasurable. In practice, decoherence explains why large objects behave classically. It does not, however, resolve the measurement problem. It tells us why we cannot see the superpositions in ordinary life. It does not tell us why measurement outcomes are definite rather than smeared. The Schrödinger equation, if applied to the entire system, including the measuring device and the environment, would predict a superposition of all possible outcomes. But we observe a single definite outcome. Why? The various interpretations of quantum mechanics answer this question differently. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the late 1920s, essentially refuses to ask it. It says that the wave function is a tool for predicting measurement outcomes, not a description of reality. The question of what happens between measurements is declared meaningless. This position has the advantage of avoiding paradoxes, but at the cost of abandoning any picture of what the world is like independent of observation. The many worlds interpretation, proposed by Hugh Everett III in 1957, takes the opposite approach. It says that the Schrödinger equation is always correct and never fails. When a measurement is performed, the wave function does not collapse. Instead, the universe splits. Every possible outcome of the measurement occurs in a separate branch of a universal wave function. We observe a single outcome because we are in one branch. The other branches, containing the other outcomes, are equally real but inaccessible to us. Many worlds has gained considerable support among physicists and philosophers of physics in recent decades because it takes the formalism seriously without any additional postulates about collapse. But it raises deep questions of its own about what probability even means when all outcomes occur, about why the branching happens along the classical axis we observe rather than some other basis, and about the nature of identity across branches. Pilot wave theory, or Bohmian mechanics, takes yet another approach. It preserves determinism and realism by postulating that particles always have definite positions, guided by the wave function acting as a pilot wave. The apparent randomness of quantum mechanics arises from our ignorance of the initial positions of the particles. This approach explicitly violates the spirit of Bell's theorem by being local. The pilot wave can propagate instantaneously, correlating distant particles, but it reproduces all quantum mechanical predictions and is therefore experimentally indistinguishable from standard quantum mechanics. None of these interpretations has been ruled out. None of them has been confirmed over the others by experiment. The question of which interpretation is correct, if that question is even well posed, remains open. What has changed dramatically in recent decades is the experimental terrain on which these questions are posed. For most of the 20th century, quantum effects were primarily visible in the behavior of individual particles, electrons, photons, and atoms. The quantum world seemed safely distant from the macroscopic world, separated by a scale barrier that was rarely crossed. That barrier is now gone. In 2025, the Nobel Prize in Physics was awarded to John Clark, Michel Deverett, and John Martinis for work demonstrating quantum mechanical behavior in superconducting electrical circuits. The significance of this recognition cannot be overstated, not just for technology, but for physics. These circuits are not microscopic. They are not made of a handful of atoms. They are macroscopic devices, circuits you can hold in your hand, that nevertheless exhibit quantum behavior, tunneling through energy barriers, occupying quantized energy levels, existing in superpositions, and being entangled with other circuits in ways that violate Bell inequalities. The original experiments that the Nobel Committee cited date to the mid-1980s, when Clark and Deverett demonstrated macroscopic quantum tunneling in superconducting devices and showed that the energy of certain circuits was quantized in exactly the way the energy levels of hydrogen atoms are Martinis extended this work and developed the experimental techniques that eventually led to the practical superconducting qubits, now used in quantum computers. What made this work possible is superconductivity. When certain materials are cooled below a critical temperature, typically within a few degrees of absolute zero, which is minus 273.15 degrees Celsius, their electrical resistance drops to exactly zero. Electrons in a superconductor do not scatter off impurities or thermal vibrations the way they do in a normal conductor. Instead, they form pairs called Cooper pairs, after the physicist Leon Cooper, who explained the mechanism. In 1956, that moved through the material as a coherent quantum state. The entire superconducting condensate behaves as a single macroscopic quantum object, described by a single wave function with a definite phase. This is not a metaphor. It is the technical description of what happens physically. The wave function of the condensate extends across the entire circuit. When the circuit is cooled and isolated from thermal noise, its behavior is governed by quantum mechanics with the same fidelity as a single electron in a hydrogen atom. The energy stored in the circuit is not continuous. It is quantized. The circuit can be prepared in a lowest energy state, excited to higher energy states, and driven to exist in superpositions of multiple energy states simultaneously. The transition between energy levels can be induced by microwave pulses, exactly as atomic transitions are induced by appropriate frequencies of light. The circuit is, in every physically meaningful sense, an artificial atom. The practical implication of this is that we now have quantum systems we can engineer. We can design the energy levels of these circuits from scratch by choosing the circuit geometry and the superconducting materials. We can build them, measure them, and integrate them into larger systems. This engineering capacity is what has driven the rapid development of superconducting quantum computing over the past 2 decades. Google's Quantum Computing Research Group, working with designs descended from Martini's original work, announced in 2019 that a superconducting quantum processor called Sycamore had performed a specific computational task in approximately 200 seconds that they estimated would require 10,000 years on the most powerful classical supercomputer available at the time. The claim was contested on methodological grounds. Classical algorithms improved, and the gap narrowed, but the underlying point remained. Superconducting quantum systems were exhibiting computational behaviors that classical systems could not efficiently replicate. The scientific significance goes deeper than computing power. The existence of macroscopic quantum systems, systems that are large enough to see, large enough to engineer, but still fully quantum in their behavior, directly addresses one of the oldest and most persistent puzzles about quantum mechanics. Why does the quantum world appear so different from the classical world? The traditional answer was scale. Quantum effects were for the small. Classical physics was for the large. But this answer was always unsatisfying because it lacked a precise boundary. Where exactly does quantum behavior stop and classical behavior begin? At what scale does indefiniteness give way to definiteness? At what point does superposition become impossible? Decoherence provides the technical answer. The transition is not sharp and is not a fundamental law. It is a consequence of environmental interactions. The larger an object is, the more interactions it has with its environment per unit time, and the faster those interactions destroy the quantum coherence of the system. A single electron in vacuum can maintain its quantum state almost indefinitely. A grain of dust in air decaheres so quickly that its quantum character is unmeasurable. But a superconducting circuit, cooled to millikelvin temperatures and isolated from electromagnetic noise, can maintain quantum coherence long enough to perform operations on its quantum state, read out the result, and repeat the experiment billions of times. This experimental program has done something conceptually important. It has demonstrated, with engineering precision, that the quantum-2 classical transition is a spectrum, not a step function. There is no magical scale at which the laws of physics change. There is only the degree of isolation from the environment. Control the isolation, and you can move any macroscopic system along the spectrum toward quantum behavior. The circuit results also have implications for one of the most surprising mathematical features of quantum mechanics: the central role of complex numbers. The wave function of a quantum system is not a real valued function. It is a complex valued function. It assigns to every possible configuration of the system a complex number, a number with both a real part and an imaginary part, where the imaginary part is multiplied by the square root of -1, denoted by the letter I. The probability of finding the system in any particular configuration is given by the squared magnitude of the complex wave function value at that configuration. But the wave function itself is inherently complex. For 100 years after quantum mechanics was developed, physicists treated this as a mathematical convenience. Complex numbers appear naturally in oscillatory systems. They are a compact way of encoding both the amplitude and the phase of an oscillating quantity. In classical physics, they are a tool that can always be traded for pairs of real numbers without any loss of content. The assumption was that quantum mechanics was the same. The complex numbers in the wave function were mathematically efficient, but not physically essential. In 2022, this assumption was tested directly and found to be wrong. A team of researchers led by Mingcheng Chen and Chaoyong Liu at the University of Science and Technology of China, working with colleagues at several institutions, performed an experiment specifically designed to distinguish between quantum mechanics formulated with complex numbers and a hypothetical alternative theory formulated entirely with real numbers. The experiment used pairs of photons prepared in specific quantum states and measured their correlations in a way designed to probe whether the interference effects produced by the complex phase of the wave function could be replicated by a real valued theory. They found that the complex quantum mechanical prediction was satisfied and the real valued alternative was violated. The result was not marginal. The violation of the real valued theory was statistically significant to the level required to rule it out as a complete description of quantum mechanics. The imaginary unit in the wave function is not a convenience. It appears to be a physical necessity. This result connects to a deep structural feature of quantum mechanics: the role of interference. When quantum systems exist in superpositions, the different components of the superposition can interfere with each other. This interference depends on the relative phases of the components, the relationship between their complex values, and produces effects that have no classical analog. The double-slit experiment is the canonical example. A single electron passing through two slits produces an interference pattern on a detector screen that reveals the wave-like character of the quantum state. No classical particle passing through one slit or the other could produce this pattern. The pattern arises because the complex amplitudes for the two paths add coherently, and their phases produce constructive interference at some locations and destructive interference at others. The real versus complex experiment shows that this phase structure, the imaginary component of the wave function, is genuinely required by nature, not merely by the formalism. You cannot replace complex amplitudes with real amplitudes and recover all of quantum mechanics. Some interference effects are only accessible to a theory that uses complex numbers, and those effects are real. They have been measured. They are present in the data. The physicists John Asher Wheeler and Rolf Landauer explored an idea decades earlier that connects the mathematical structure of quantum mechanics to a more radical claim: that information is not just a useful way of describing physical systems, but is itself physically fundamental. Wheeler summarized this in a phrase he coined: it from bit. The idea was that every physical quantity, every item of physical reality, derives its existence from answers to binary questions. The world, at its most fundamental level, might be made of information rather than matter. This is not the standard interpretation of quantum mechanics, and it is not what experiments directly confirm, but it is taken seriously by a significant number of physicists and has motivated research programs in quantum information theory that have generated concrete physical insights. The perspective that information is physically real, that it has thermodynamic consequences, that it obeys conservation laws in certain contexts, and that it imposes limits on physical processes, has proven technically productive. Rolf Landauer made one of the most concrete contributions to this program in 1960, when he argued that the erasure of information must be accompanied by the dissipation of heat. When a bit of information is erased, when a memory register is reset from an unknown state to a known state, the entropy of the information system decreases. But the second law of thermodynamics requires that entropy never decrease in an isolated system. Therefore, erasing a bit must generate heat in the surrounding environment. The minimum amount of heat generated per erased bit is called the Landauer limit, and it equals the temperature in Kelvin, multiplied by Boltzmann's constant, multiplied by the natural logarithm of 2 at room temperature. This is approximately 2.8 times 10 to the minus 21 joules per bit, an incredibly tiny amount. But as computing devices shrink and operate at higher densities, they approach this limit. It has been verified experimentally. It connects the abstract concept of information to a concrete physical quantity, heat. Information is not merely an abstraction. It has physical consequences. This connection between information and physics extends to one of the most dramatic thought experiments in modern physics: the black hole information paradox. Black holes are regions of space-time where gravity is so intense that not even light can escape. They form when massive stars collapse at the end of their lives, or through other mechanisms involving the concentration of sufficient mass in a small enough region. The boundary of a black hole, the point of no return, beyond which nothing can escape, is called the event horizon. In 1974, Stephen Hawking showed that black holes are not completely black. Quantum effects near the event horizon cause black holes to emit thermal radiation, now called Hawking radiation, with a temperature inversely proportional to the black hole's mass. A stellar mass black hole has a Hawking temperature so low it is unmeasurable, but the process is predicted to eventually cause any black hole to evaporate completely over an astronomical timescale. The paradox arises from the character of this radiation. Hawking calculated that the radiation is exactly thermal. It carries no information about what fell into the black hole. A black hole that swallows a library and one that swallows the same mass in hydrogen gas would both emit identical Hawking radiation. When the black hole finally evaporates, all the information about what it consumed appears to be gone. This violates a fundamental principle of quantum mechanics: unitarity. Quantum mechanical evolution is described by unitary operators, which are mathematically reversible. Given the final state of a quantum system, you can, in principle, reconstruct the initial state by running the evolution backward. No information is truly lost in quantum mechanics. It may become scrambled and practically inaccessible, but it is never destroyed. If Hawking's calculation is correct and black hole evaporation destroys information, then either quantum mechanics is wrong or general relativity is wrong, or both need to be modified in some deep way. The reconciliation of these two theories, quantum mechanics and general relativity, is the central unsolved problem of theoretical physics, and the black hole information paradox is one of its sharpest manifestations. Recent work has suggested that information is not lost. Calculations using the holographic principle, the idea that the information content of a region of space-time is encoded on its boundary rather than in its bulk, suggest that Hawking radiation is actually very slightly non-thermal, carrying information in subtle correlations between the emitted photons. The radiation looks thermal, but it is not exactly thermal. The information survives, hidden in correlations that are practically impossible to extract, but are there in principle. The calculation that demonstrated this, developed in the early 2020s by Ahmed Netta Engelhardt, Donald Maralf, and Henry Maxfield, and by others working in the framework of the ADS-CFT correspondence, shows that the entropy of the Hawking radiation follows what is called the Page curve, rising for the first half of the black hole's lifetime and then decreasing as the information stored in the hole is gradually transferred to the radiation. This behavior is consistent with unitarity and suggests that quantum mechanics survives intact even in the extreme context of black hole evaporation. The calculation is not complete in the sense of providing a full account of how the information escapes. It relies on techniques from string theory and holography that are not fully established in all the contexts needed, but it represents the most concrete progress on the information paradox in decades, and it points toward a picture in which information is truly indestructible, of conserved quantity of the universe. The question of what space and time are at the quantum level is where many of these threads converge. Classical general relativity describes space-time as a smooth, four-dimensional manifold, a geometric structure that can be curved by the presence of mass and energy. Quantum mechanics, as currently formulated, requires a fixed background space-time in which quantum fields live and evolve. The two theories are fundamentally incompatible at this structural level. Combining them requires either quantizing space-time itself, which leads to serious technical problems, or finding a different, conceptual framework in which both emerge as approximations to something more fundamental. Loop quantum gravity. One of the leading approaches to quantum gravity proposes that space-time itself is quantized at the Planck scale, the scale at which quantum gravitational effects become significant. Approximately 1.6 times 10 to the minus 35 meters. Below this scale, the notion of a smooth, continuous space-time breaks down. Instead, space-time is made of discrete units, loops and networks of quantum geometry, and the smooth space-time of general relativity emerges from the collective behavior of these discrete elements. At larger scales, dot string theory, another approach, proposes that the fundamental constituents of nature are not point particles, but one-dimensional, extended objects, strings, whose different vibrational modes correspond to different particles. String theory naturally includes gravity and provides a consistent quantum theory of all forces, but it requires extra spatial dimensions beyond the three we observe. The extra dimensions are thought to be compact, curled up at scales too small to detect with current experiments. Both of these approaches are research programs, not confirmed theories. Neither has made distinctive, testable predictions that have been confirmed experimentally. Both have generated mathematical insights, some of which like the connections between quantum entanglement and the geometry of spacetime developed through the study of holography, have influenced thinking about the foundations of physics in ways that go beyond the specific theories themselves. The deepest of these insights may be the connection between entanglement and geometry in the framework of the ADS-CFT correspondence introduced by Juan Maldacena in a quantum theory without gravity. Living on the boundary of a region of space-time is exactly equivalent to a theory with gravity inside that region. The geometry of the interior is encoded in the correlations, specifically the entanglement structure of the boundary theory, work by Mark van Romstank in 2010, and subsequent developments, has suggested that entanglement is not just a byproduct of quantum mechanics, but a structural component of spacetime itself. When two regions of a boundary quantum theory are entangled, their corresponding regions of interior spacetime are geometrically connected. When the entanglement between two parts of the boundary theory is cut, the corresponding interior spacetime literally disconnects. It splits into two separate pieces. Spacetime, in this picture, is woven from quantum entanglement. This is a hypothesis, not a confirmed result, but it is a specific, mathematically precise hypothesis that makes contact with established frameworks and has been developed in enough detail to motivate concrete calculations. If it is correct, it means that the geometry of space and time is not fundamental. It is emergent. It arises from the pattern of correlations in an underlying quantum system, just as the smoothness of a block of wood arises from the collective behavior of its atoms. The implications for what reality is run deep. If space-time is emergent, then asking what reality is like at scales below the Planck length is like asking what a crystal is like at scales smaller than the lattice spacing. The question may not have an answer because the concepts that define the question, position, distance, geometry, no longer apply. The properties of time present a related challenge. In classical physics, time is a parameter, a background variable against which things change. In general relativity, time is part of spacetime and can be curved, stretched, and slowed by gravity. But in quantum mechanics, time is treated differently from position. Position is a quantum observable, a property of a system that can be measured and that is associated with a Hermitian operator. Time is not. In the Schrödinger equation, time is a parameter, not an observable. There is no time operator in standard quantum mechanics. This asymmetry becomes acute when you try to combine quantum mechanics with general relativity. In general relativity, the time coordinate is relative. It depends on the reference frame and the gravitational field. In quantum mechanics, time is absolute and external. Reconciling these two treatments of time is one of the core technical challenges of quantum gravity. The Wheeler-DeWitt equation, derived by John Wheeler and Bryce DeWitt in the 1960s as an attempt to quantize the gravitational field, produces a striking result. The equation does not contain a time parameter, the wave function of the universe, if such a concept is meaningful, does not evolve in time. The wave function simply is, and what we experience as the flow of time is somehow encoded in the relational structure of the wave function's spatial components. This is called the problem of time in quantum gravity, and it remains unsolved. It suggests that at the most fundamental level, time may not be a primitive aspect of reality. Like space, it may be emergent, the experience of duration, of things happening in sequence, may be a feature of how quantum systems of sufficient complexity perceive their own entanglement structure, not a feature of the underlying quantum state itself. The Italian theoretical physicist Carlo Rovelli has developed this idea into what he calls the relational interpretation of quantum mechanics. in which physical properties are not defined absolutely but only relative to other systems. A particle does not have a definite spin in isolation. It has a definite spin relative to whatever system interacted with it. Different systems may have different facts about the same particle, and there is no absolute fact of the matter. Reality, in this view, is irreducibly relational. This interpretation dissolves certain paradoxes of quantum mechanics, including the measurement problem, in a certain sense, but raises new questions about consistency and about how a coherent shared experience of the world arises from a collection of relative descriptions. It has been developed with mathematical rigor and is taken seriously by a growing number of physicists and philosophers of physics. What unites all of these developments, the Bell experiments, the macroscopic quantum circuits, the imaginary number tests, the information paradox, the entanglement and geometry connection, the problem of time, is a progressive dismantling of assumptions that seemed obvious but were never verified. We assumed that physical properties were definite before measurement. Bell's theorem and its experimental tests showed that assumption is false if we also require locality. We assumed that quantum behavior was confined to the microscopic. Superconducting quantum circuits showed that assumption is an artifact of decoherence, not a law of nature. We assumed that the complex numbers in quantum mechanics were mathematical conveniences. The 2022 experiment showed that they are physically required. We assumed that information could be destroyed. The page curve calculation suggests it cannot, even inside a black hole. We assumed that space-time was fundamental. The holographic evidence suggests it may be emergent. We assumed that time was a primitive feature of the universe. The problem of time in quantum gravity suggests it may not be. Each of these assumptions seemed so natural, so consistent with ordinary experience, that questioning them felt unnecessary. And each of them has turned out to be wrong, or at least profoundly incomplete. When confronted with careful measurement and consistent theoretical analysis, this pattern is worth reflecting on. The history of physics is substantially a history of discarding obvious assumptions. It was obvious that the Earth was stationary. It was obvious that space and time were absolute. It was obvious that the speed of light should depend on the motion of the observer. Each of these obvious things turned out not to be true. Quantum mechanics represents perhaps the most radical step in this direction, not a revision of specific beliefs about the world, but a challenge to the entire framework by which we form beliefs about the world. The concept of objective reality, the idea that the world has a definite state independent of any observer or measurement, is precisely what quantum mechanics calls into question. The phrase objective reality is not usually treated as a scientific hypothesis. It is treated as a precondition for doing science. You cannot measure what does not exist. You cannot verify what has no definite state. But quantum mechanics, as an operational matter, requires that we work with states that are not definite until measured. The theory that best describes reality does not assume that reality is definite. Different interpretations handle this in different ways. Copenhagen says to stop asking. Many worlds says all outcomes are real in some branch. Bohmian mechanics says reality is definite, but relational quantum mechanics says properties are only defined relative to other systems. Cubism, quantum Bayesianism, says the wave function is an agent's beliefs about measurement outcomes, not a description of external reality. None of these is the consensus view. Polls of physicists on their preferred interpretation produce results scattered across all options, with plurality support shifting over time and varying by generation. The question of which interpretation is correct, whether that question is meaningful, is open. What is not open is the empirical content. The predictions of quantum mechanics are verified to extraordinary precision. The Bell inequality violations are real. The macroscopic quantum circuits work. The computational advantages of quantum systems are being demonstrated in laboratories around the world. Whatever quantum mechanics means, it correctly describes what the world does. The research frontier today is pushing in several directions simultaneously. In quantum computing, the challenge is scaling superconducting qubit systems to the hundreds of thousands of physical qubits needed for fault-tolerant computation, while reducing error rates and improving qubit coherence times. The threshold for fault-tolerant quantum computation using surface codes, a class of quantum error-correcting codes that require only local operations, has been analyzed in detail. Achieving it requires physical qubit error rates below approximately 1% per operation. Current superconducting qubit systems are approaching this threshold from above, with error rates in the range of fractions of a percent for the best systems. In quantum foundations, experimental tests are growing more sophisticated. Tests of Bell inequalities using entangled photons separated by kilometers, with detection events space-like separated to close the locality loophole, are now routine. Tests using atoms, molecules, and solid-state systems are extending the range of physical systems where quantum non-locality has been confirmed. Experiments targeting specific interpretational questions, such as the Wigner's friend scenarios, which test whether different observers can have genuinely contradictory facts about the same quantum event, are moving from thought experiment to laboratory reality in quantum gravity. The holographic correspondence between entanglement and geometry is being explored with increasing mathematical depth. The connection between quantum error correction and the structure of holographic spacetime, first noticed by Ahmed Elmhiri, Shidong, and Daniel Harlow in 2014, suggests that the geometric structure of spacetime in the holographic interior is encoded in the error-correcting properties of the boundary quantum state. The redundancy that error correction requires is mapped onto the redundancy of the holographic encoding. This is a striking and specific connection between the information theory of quantum error correction and the quantometry of quantum gravity. What remains genuinely unknown is large. We do not know what the correct interpretation of quantum mechanics is. If that question has a unique answer, we do not know how to consistently combine quantum mechanics and general relativity at all energy scales. We do not know whether time and space are fundamental or emergent, and if emergent, from what they emerge. We do not know whether the universe's initial quantum state selected for the specific physical constants and laws we observe, or whether those constants are fixed by some deeper principle, or whether they vary across some multiverse of possible universes. We do not know, in a deep sense, what the wave function is. Is it a real physical field pervading three-dimensional space? Is it a property of an abstract high-dimensional configuration space? Is it a representation of our knowledge, or of the world, or of both? The answer to this question would tell us what reality is made of at the quantum level, and we do not have it. What we do have is an extraordinarily successful theory, whose predictions have never been wrong in any domain where they have been tested. We have experimental tools that can isolate quantum systems at macroscopic scales. We have mathematical frameworks that connect gravity, information, and quantum mechanics in ways that are suggestive, if not yet complete. We have philosophical analyses that have clarified what the genuine puzzles are and what would count as solving them. The trajectory of the field is toward deeper integration. The walls between quantum computing, quantum foundations, and quantum gravity are porous. An insight about quantum error correction in a superconducting circuit can turn out to have implications for the structure of spacetime. An experiment on Bell inequalities in a laboratory can constrain what kinds of hidden variable theories are consistent with observations at cosmological scales. A calculation about information flow in a black hole can shed light on why the wave function must be complex. Science does not usually progress by answering the biggest questions directly. It progresses by making those questions precise, identifying the specific places where existing frameworks break, and building the experimental and theoretical tools that make new frameworks possible. By that measure, the current period in quantum physics is exceptionally productive. For a century, quantum mechanics has worked without anyone being entirely sure what it means. The calculations work. The predictions are confirmed. The technology, from transistors and lasers to MRI machines and superconducting quantum computers, is built on quantum foundations. But the conceptual picture, the answer to the question of what the world is actually like at the quantum level, remains unfinished. That is not a weakness of the field. It is a reflection of how genuinely hard the question is. When the data forces you to abandon the assumption of objective, definite reality, you are not just revising a belief. You are questioning the framework within which beliefs about the world are formed. That kind of revision takes time. It requires not just new experiments, but new ways of thinking. The experiments keep coming. The macroscopic quantum circuits demonstrated that the quantum classical divide is not a law of nature. The Bell inequality violations established that local hidden variable theories cannot account for quantum correlations. The imaginary number experiment showed that complex numbers are physically necessary, not merely mathematically convenient. The page curve calculations suggested that information survives black hole evaporation. The holographic principle suggests that space-time itself may be woven from quantum entanglement. The picture that emerges from these results is consistent but strange. Reality, at its most fundamental level, does not consist of objects with definite properties moving through a fixed space-time background. It appears to consist of quantum states, complex probability amplitudes, whose definiteness is relative, contextual, and dependent on interactions. The space-time background itself may be an approximate description, accurate at large scales but dissolving at small scales into something more abstract, a pattern of quantum correlations, a structure of entanglement, an information theoretic network from which geometry and time and matter emerge. This is not the world our instincts prepared us to inhabit, but instincts were shaped by the scales and speeds at which human organisms navigate a macroscopic, slow-moving, decoherence-dominated environment. There is no reason to expect those instincts to correctly model the behavior of photons, electrons, or the geometry of space-time at the Planck scale. The surprise is not that quantum mechanics is strange. The surprise is that we managed to discover it at all, that the experimental and mathematical tools available to a species with macroscopic intuitions were sufficient to push through the scales of decoherence, isolate quantum systems, and measure their behavior accurately enough to reveal what was hidden there. What remains to be discovered is the picture underneath the quantum formalism itself. Quantum mechanics, as it stands, is a recipe for computing probabilities. It works with extraordinary precision, but it does not obviously tell a story about what the world is doing between measurements. The story that it tells, if forced, a story about superpositions of all possible outcomes, about complex amplitudes that interfere, about entanglement that can exceed any local classical correlation, is a story unlike anything in the history of science. The question that quantum mechanics raises, more than any specific experimental result, is whether the universe is the kind of thing that has a story at all, whether there is a description of what is actually happening, independent of any observer or measurement, whether reality at the quantum level is even coherent in the sense we expect. Those questions are still open. The experiments that will bear on them are still being designed. The mathematics that might resolve them is still being developed. And somewhere in that gap between the perfectly accurate predictions of quantum mechanics and the still absent understanding of what those predictions mean, the deepest revision in our concept of reality is still waiting to be completed. If you want to follow the research as it develops, as the circuits get more coherent, the experiments more precise, and the theoretical picture more complete, staying with this subject means staying at the edge of what physics currently knows and does not know. That edge is moving fast, and the questions being asked there are among the most important questions about the nature of reality that science has ever seriously addressed. To understand how far the field has come, it helps to trace the history of how these ideas developed, not as a sequence of isolated discoveries, but as a progressive confrontation with the inadequacy of classical concepts applied to the behavior of very small things. In the late 19th century, physics appeared to be nearly complete. Newton's laws of motion and his theory of gravity had stood for more than 200 years. Maxwell's equations, published in 18, unified electricity and magnetism and predicted the existence of electromagnetic waves, including light, as self-propagating oscillations of electric and magnetic fields. Thermodynamics and statistical mechanics had connected the macroscopic behavior of heat and temperature to the microscopic behavior of atoms and molecules. The tools seemed sufficient. The cracks appeared in specific, precise measurements. One was the problem of black body radiation. A black body is an idealized object that absorbs all radiation that falls on it and emits radiation purely as a function of its temperature. Classical physics predicted the spectral distribution of that radiation, how much energy should be emitted at each frequency, using statistical mechanics applied to the electromagnetic field inside the body. The prediction worked reasonably well at low frequencies, but diverged catastrophically at high frequencies. The classical formula predicted infinite energy emission at very short wavelengths. This was so obviously wrong that physicists called it the ultraviolet catastrophe. Max Planck solved the problem in 1900, but only by introducing an assumption that had no classical justification. He proposed that electromagnetic radiation was emitted and absorbed, not continuously, but in discrete packets. Quanta, each carrying an energy proportional to its frequency. The proportionality constant, now called Planck's constant and denoted by the letter h, is approximately 6.626 times 10 to the minus 34 joule-seconds. This is an extraordinarily small number, which is why quantum effects are invisible in everyday life. But at the scale of atoms and photons, it dominates. Planck himself was uncomfortable with the assumption. He viewed it as a mathematical trick to fit the data, not a physical claim about the nature of light. Einstein took it further. In 1905, the same year he published his paper on special relativity, Einstein proposed that light was not just emitted and absorbed in quanta, it was composed of quanta. What we call photons are discrete packets of electromagnetic energy, each carrying an energy equal to Planck's constant, multiplied by the frequency of the light. Einstein used this to explain the photoelectric effect. When light falls on a metal surface, electrons are ejected, but only if the light's frequency exceeds a threshold value that depends on the metal, regardless of the intensity of the light. Classical wave theory predicted that intensity should determine whether electrons were ejected. A brighter light should always be able to eject electrons eventually, but experiments showed the opposite. Dim, high-frequency light ejected electrons immediately, while intense low-frequency light ejected none. Einstein's photon model explained this cleanly. Only a photon with energy above the threshold, meaning frequency above the threshold, could knock an electron free. More photons meant more electrons ejected. But no electron could accumulate energy from multiple photons to overcome a threshold it could not cross. Individually, Einstein received the Nobel Prize in Physics in 1921, specifically for his explanation of the photoelectric effect, not for special relativity or general relativity, which are the discoveries most associated with his name in popular accounts. The committee considered the photon model the more rigorously established contribution at that time. Niels Bohr applied quantization to atomic structure in 1913. The classical model of the atom predicted that electrons orbiting a nucleus should continuously radiate energy, spiral inward, and collapse into the nucleus within a fraction of a nanosecond. Real atoms do not do this. Bohr proposed that electrons could only occupy specific discrete orbits, orbits in which the angular momentum of the electron was an integer multiple of Planck's constant divided by 2 pi. Electrons in these allowed orbits did not radiate. They only radiated when they jumped from a higher orbit to a lower one, emitting a photon with energy equal to the difference between the two orbital energies. Bohr's model correctly predicted the spectral lines of hydrogen, the specific frequencies of light emitted by excited hydrogen atoms, to remarkable precision. It was a phenomenological success, but it offered no explanation for why only certain orbits were allowed. The rule was imposed by hand, not derived from any deeper principle. The deeper principle came from Louis de Broglie in 19. He proposed that just as light, understood as a wave, had particle-like properties, electrons, understood as particles, might have wave-like properties. The wavelength of an electron would be related to its momentum by the same relationship that connected photon energy to frequency. The de Broglie wavelength equals Planck's constant divided by the momentum. If electrons had wavelengths, then Bohr's allowed orbits were simply those in which an integer number of electron wavelengths fit around the orbit's circumference, a condition for standing waves, analogous to the harmonics of a vibrating string. Today, Broglie's hypothesis was confirmed experimentally in 1927 by Clinton Davison and Lester Germer, who showed that electrons scattered from a crystal lattice produced diffraction patterns, the same patterns that X-rays, known waves, produced under similar conditions. Electrons were interfering with each other like waves. The particle-wave duality was not an artifact of light's special nature. It was a general feature of quantum entities. Werner Heisenberg formulated quantum mechanics mathematically in 1925 using a framework called matrix mechanics, in which physical observables were represented by matrices and their time evolution was governed by matrix equations. Erwin Schrödinger reformulated the theory in 1926 using the wave equation that now bears his name, which described how the probability amplitude of finding a particle at a given location evolved over time. Paul Dirac showed that the two formulations were mathematically equivalent, different representations of the same underlying structure. Heisenberg derived from his formulation one of the most famous results in physics, the uncertainty principle. For any two observables that do not commute, whose matrix representations do not multiply to the same result in both orders, there is a fundamental limit on how precisely both can be simultaneously known for position and momentum. The product of the uncertainties in the two quantities must be at least equal to Planck's constant divided by 4 times pi. This is not a statement about measurement disturbance, not a claim that measuring position disrupts momentum in a way that could, in principle, be corrected. It is a statement about the quantum state itself. A state with a definite position has no definite momentum. A state with a definite momentum is spread across all of space. This was not a feature of early quantum mechanics, that physicists expected to find permanent. Many of them, including Einstein, assumed that it reflected an incompleteness in the theory. Perhaps a more complete theory would restore definite values to both position and momentum simultaneously. Einstein spent much of the latter part of his career attempting to find such a theory and arguing that quantum mechanics, precisely because of its statistical character, could not be the final word. His most famous challenge was the EPR paper, published in 1935, with Boris Podolsky and Nathan Rosen. Einstein, Podolsky, and Rosen constructed a thought experiment involving two particles that had interacted and then separated. If you measured the position of one particle precisely, you could infer the position of the other without disturbing it. If you measured the momentum of one, you could infer the momentum of the other, since neither measurement disturbed the second particle. Einstein argued the second particle must have had definite values for both position and momentum before any measurement was made, contradicting the quantum mechanical claim that these properties were undefined. Bohr responded to EP, but his response was widely regarded as obscure and difficult to interpret. The conceptual debate dragged on for decades without resolution. Bell's theorem, derived in 1964, was the decisive move that turned the debate from philosophy to physics. By deriving a mathematical inequality that any local hidden variable theory must satisfy, Bell showed that the dispute could be settled by experiment. If quantum mechanics was correct, the inequality would be violated. If local realism was correct, it would not. The experimental tests that followed by Jean Clauser and colleagues in the early 1970s, by Auling Aspect and colleagues in 1982, by Gregor Wies and colleagues in 1998, and by many subsequent groups using increasingly sophisticated apparatus, all confirmed the quantum mechanical prediction. Bell's inequality was violated. Consistently, and by the amounts that quantum mechanics predicted, the 2022 Nobel Prize awarded to Clauser Aspect and Zeilinger recognized not just these specific experiments but the entire program of experimental quantum foundations that they established. The prize acknowledged that the question of whether quantum mechanics could be completed by a local hidden variable theory had been settled experimentally, not just theoretically. The answer was no. What the Bell experiments established is more subtle than it might appear. They did not prove that there are no hidden variables. They proved that no local hidden variable theory can reproduce quantum mechanical predictions. Non-local, hidden variable theories, like Bohmian mechanics, remain viable. But locality and realism cannot both be maintained simultaneously. This creates a stark choice. Either the world is non-local, events at one location can be instantaneously connected to events at arbitrarily distant locations, or the world is not. Physical properties do not have definite values, independent of measurement. Most working physicists accept non-realism. Quantum mechanics does not assign definite values to unmeasured quantities, and that is simply how the world is. But a significant minority maintains that non-local realism is the more coherent position, even though it requires abandoning relativistic locality in some sense. The non-locality involved in quantum entanglement is subtle. It does not allow information to be transmitted faster than light. The correlations between distant entangled particles are real and exceed what local classical correlations could produce, but they cannot be used to send a message. You cannot choose what outcome you get when you measure your particle, so you cannot encode a message in the correlation. The non-locality is genuine in the sense of violating Bell's inequality, but it is signaling neutral. It produces no detectable signal from one measurement location to the other. This fact has been carefully verified. Attempts to use quantum entanglement for faster-than-light communication have failed, not due to technical limitations, but due to the fundamental structure of the theory. The no-communication theorem, a mathematical result derived from the formalism of quantum mechanics, PROVES, that correlations between entangled particles cannot be used to transmit information faster than light. This preserves compatibility with special relativity at the operational level, even as it violates Bell's locality condition at the correlational level. The tension between quantum non-locality and relativistic locality is one of the reasons that a fully quantum theory of gravity remains so difficult. General relativity is a local theory. The curvature of spacetime at any point is determined by the energy and momentum there, and information propagates only as fast as light. Quantum mechanics, while operationally compatible with special relativity in the framework of quantum field theory, has the non-local correlational structure revealed by Bell experiments embedded in it. A theory that combines both frameworks must somehow accommodate both the local causal structure of relativity and the non-local correlational structure of quantum mechanics. Quantum field theory, the framework that combines quantum mechanics with special relativity, achieves this at the level of field operators by requiring that operators associated with space-like separated regions must commute. Commutativity ensures that measurements at one location cannot affect measurement outcomes at a distant, space-like, separated location. The non-local correlations between entangled particles are consistent with this because, as the no-communication theorem shows, they cannot be used for signaling. But the conceptual tension between the non-local correlational structure and the local dynamical structure of quantum field theory remains a source of interpretational difficulty. Beyond these foundational puzzles, quantum mechanics has spawned a technological revolution that is still accelerating. The first quantum revolution, as it is sometimes called, encompassed the technologies that emerged from early quantum theory: transistors, which depend on quantum mechanical tunneling and band structure; lasers, which depend on stimulated emission as described by Einstein's quantum theory of radiation; and MRI machines, which depend on nuclear magnetic resonance, a quantum mechanical phenomenon involving the alignment and precession of nuclear spins in magnetic fields. These technologies collectively transformed the world over the second half of the 20th century and continue to underpin the global economy. Every microprocessor ever made depends on quantum mechanics. Every laser, from the one in your optical drive to the ones used in fiber optic communications, depends on quantum mechanics. Every semiconductor device depends on quantum mechanics. The first quantum revolution is not a historical event. It is the ongoing foundation of modern technology. The second quantum revolution is now beginning. It is distinguished from the first by its use of specifically quantum phenomena, superposition, entanglement, and quantum measurement as computational and communications resources, rather than merely as background physics that enables devices to function. The first revolution exploited quantum mechanics without controlling individual quantum states. The second revolution is built on the ability to prepare, manipulate, and measure individual quantum states with high fidelity. Quantum computing is the most prominent application of the second revolution. A quantum computer uses quantum bits, or qubits, instead of classical bits. A classical bit is always either 0 or 1. A qubit can be in a superposition of 0 and 1 simultaneously, with complex amplitudes for each. When a qubit is measured, it collapses to either 0 or 1, with probabilities given by the squared magnitudes of the amplitudes. The quantum advantage comes from the ability to manipulate many qubits simultaneously in ways that exploit interference and entanglement to solve certain computational problems faster than any known classical algorithm. The most famous quantum algorithm is Shor's algorithm. published by Peter Shaw in 1994. It can factor large integers in polynomial time, a time that grows only polynomially with the number of digits of the integer. The best-known classical algorithms for factoring require exponential time, the security of widely used public key cryptographic systems, including the RSA algorithm that underlies much of Internet security, depends on the presumed difficulty of factoring large integers. A large-scale quantum computer running Shaw's algorithm would render these cryptographic systems vulnerable. This potential threat has driven substantial investment in post-quantum cryptography, cryptographic algorithms that are believed to be secure against both classical and quantum attacks. The United States National Institute of Standards and Technology finalized its first set of post-quantum cryptographic standards in 2024, selecting algorithms based on mathematical problems believed to be hard even for quantum computers. The transition to post-quantum cryptography is a significant ongoing engineering challenge for organizations that handle sensitive data. Grover's algorithm, also developed by Loaf Grover in 1996, provides a quadratic speedup for unstructured search problems. If you have a list of 100 trillion items and want to find one with a specific property, a classical computer requires, on average, 50 trillion steps. Grover's algorithm requires only about 10 million steps, the square root of the list size. While a quadratic speedup is less dramatic than Shaw's exponential speedup, it has broad applicability to optimization problems that arise throughout science and industry. The current generation of quantum computers, while not yet at the scale required to run Shaw's algorithm on cryptographically relevant integers, is already producing scientific results. Quantum processors have been used to simulate the behavior of quantum chemical systems, calculating the ground state energies of small molecules with accuracy that is difficult to achieve classically. This application is widely seen as the most near-term, commercially valuable use of quantum computers. Molecular simulation for drug discovery, materials, science, and catalyst design, where the relevant systems are inherently quantum, and their simulation is exponentially hard for classical computers. Quantum communication is another active area. Quantum key distribution uses the properties of quantum states to establish a shared cryptographic key between two parties with information theoretic security. The security follows from the laws of physics, not from computational assumptions. If an eavesdropper tries to intercept the quantum states used to establish the key, the act of interception necessarily disturbs the states in a detectable way. The legitimate parties can detect the eavesdropping and discard the compromised key material. Quantum networks, networks of quantum devices connected by quantum communication channels, are under development by research groups and national programs in Europe, China, the United States, Japan, and elsewhere. China demonstrated in 2020 a quantum satellite called Mesius that distributed entangled photon pairs between ground stations more than 1,000 kilometers apart, establishing entanglement at a scale not previously achieved. The goal is eventually to build a quantum internet, a network over which quantum states can be transmitted, distributed, and processed, enabling new forms of secure communication and distributed quantum computing. Quantum sensing represents a third pillar of the second quantum revolution. Quantum sensors exploit the sensitivity of quantum states to external perturbations to make measurements with precision that exceeds what classical devices can achieve. Atomic clocks, which use the precise quantum mechanical frequency of atomic transitions as a frequency reference, already represent a form of quantum sensing. The most precise atomic clocks, based on optical transitions in strontium or ytterbium atoms, are accurate to better than 1 part in 10 to the 18th. They would neither gain nor lose a second over the age of the universe. Quantum gravimeters use atom interferometry to measure the local gravitational field with extreme sensitivity. Since gravity depends on the distribution of mass, a sufficiently sensitive gravimeter can detect underground structures, map subsurface geology, and monitor small changes in Earth's gravitational field. These applications have uses in navigation, oil and gas exploration, earthquake monitoring, and fundamental measurements of gravitational physics. Quantum magnetometers, using nitrogen vacancy centers in diamond or atomic vapors, can measure magnetic fields with sensitivity approaching the fundamental quantum limit. Applications include the detection of magnetic anomalies in archaeological surveys, the mapping of brain magnetic fields in magneto, and the detection of biomagnetic signals from the heart and nervous system. All of these technologies trace directly to the quantum mechanical phenomena, identified in the first decades of the 20th century and demonstrated in macroscopic engineered systems in the decades since. The progression from fundamental physics to technological application is not linear. It involves engineering breakthroughs, materials, science, and the development of cryogenic and laser cooling techniques that were themselves major research programs. But the trajectory is clear. The deeper our understanding of quantum mechanics has become, and the more precisely we can control quantum systems, the more powerful the resulting technology. There is a deeper point here that connects the technology back to the foundations. The ability to build and operate quantum technologies at the level of individual quantum states has given physicists a tool for testing quantum mechanics itself in regimes that were previously inaccessible. Superconducting qubits, ion traps, photonic circuits, and nitrogen vacancy centers are not just potential computing devices. They are quantum systems with a degree of control and measurement fidelity that allows tests of quantum mechanics at a precision and in a context that no earlier generation of experiments could achieve. When John Martini's group demonstrated that a superconducting qubit system showed quantum behavior, they were not just building a quantum computer. They were demonstrating that quantum mechanics applied to a macroscopic circuit in ways that had been theorized but never directly confirmed. When photon pairs are used to test Bell inequalities with detection loophole closed, the experimenters are not just verifying known physics, they are establishing, with new levels of rigor, that the world genuinely violates local realism at the level that quantum mechanics predicts. The reciprocal relationship between technology, development, and fundamental physics testing is one of the hallmarks of modern physics. Each improvement in quantum device technology enables more precise tests of quantum foundations. Each insight from quantum foundations constrains and guides the development of quantum technology. The field is unusually integrated. Fundamental questions and engineering applications are pursued by overlapping communities using the same experimental platforms. This integration has not dissolved the deep conceptual puzzles of quantum mechanics. The measurement problem is not solved by better quantum computers. The preferred basis problem, the question of why measurement outcomes occur in the specific basis associated with classical pointer states rather than some other quantum basis, is not addressed by more precise Bell tests. The interpretation question, the question of what the wave function is and what quantum mechanics says about reality, is not resolved by any currently foreseeable experiment, because most interpretations are empirically equivalent by construction. What the technological progress has done is establish beyond any reasonable doubt that quantum mechanics is the correct framework for describing physical systems at the scales it has been tested, and that there is no classical underlying reality from which the quantum description emerges. The precision of quantum mechanical predictions from the anomalous magnetic moment of the electron, which matches experiment 212 decimal places to the spectral lines of hydrogen, to the behavior of superconducting quantum circuits leaves no room for an underlying classical theory to hide. This precision is itself a kind of philosophical result. A theory that works to 12 decimal places across a vast range of physical systems and energy scales is not a theory that could be improved by a small modification. Any replacement theory would need to reproduce all these predictions, exactly while making different predictions somewhere that experiments could distinguish. The known attempts at such theories, hidden variable theories, collapse theories like the Garadi-Riemann-Weber model, various modified versions of the Schrödinger equation, have all either been shown to be equivalent to quantum mechanics in all tested regimes, or have been constrained by experiments into versions that differ from quantum mechanics only at scales far beyond current experimental access. The GRW collapse model, proposed by Giancarlo Garadi, Alberto Rimini, and Tullio Weber in 1986, is one of the most serious attempts to provide a physical explanation for the measurement problem without resorting to many worlds or hidden variables. It modifies the Schrödinger equation by adding random spontaneous localization events, collapses of the wave function to localize states that occur at a rate too slow to be detectable for individual particles, but fast enough when the system contains macroscopic numbers of particles to ensure that macroscopic superpositions collapse quickly. The model has definite predictions. The random localization events add a tiny amount of noise to the dynamics of any quantum system, and this noise is in principle measurable. Experiments searching for this excess noise in low temperature, mechanical oscillators and other systems have constrained the GRW parameters and ruled out large regions of the original parameter space. The model is not ruled out entirely, but it has been pushed into a corner where its parameters must be chosen carefully to avoid conflict with existing data. Refined experiments in the next decade will test it further. Another class of modifications involves continuous spontaneous localization, or CSL, which generalizes the GRW approach. These models predict that quantum superpositions in macroscopic systems collapse at a rate that depends on the spatial extent of the superposition. A superposition in which two states differ only in the position of a single electron collapses very slowly. A superposition in which two states differ in the position of a gram of material collapses essentially instantaneously. The threshold for classical behavior is the macroscopic scale, not a fixed particle number. Testing these models requires preparing large quantum superpositions and measuring how long they persist. The coherence time. Experiments using interferometry with large molecules have pushed the mass scale of observed quantum superpositions progressively higher. Molecules of a few thousand atomic mass units have been shown to produce interference patterns, demonstrating that their quantum coherence was maintained over the course of the experiment. Extending these experiments to ever larger molecules and eventually to nanoparticles is an active research area, specifically motivated by the desire to test whether the quantum-to-classical transition is governed by a modification of the Schrödinger equation or purely by decoherence. If collapse models are correct, there should be a mass scale above which quantum interference becomes impossible regardless of how well the system is isolated from the environment. If standard quantum mechanics plus decoherence is correct, the transition to apparent classical behavior should be entirely explicable in terms of environmental interactions, with no fundamental scale at which quantum mechanics breaks down. Current experiments have not reached the regime where these predictions diverge significantly, but the trajectory is clear, and the experiments will get there. The philosophical stakes of this experimental program are unusually high. If a collapse model is confirmed, if quantum mechanics must be modified to explain why macroscopic superpositions do not persist, then the wave function is not just a calculation tool. Something physically real is causing it to collapse. The question of what that something is and how it is triggered would be a new open question at the frontier of physics. If collapse models continue to be excluded, and quantum mechanics turns out to be correct at all tested scales with no modifications, then the measurement problem remains in the domain of interpretation rather than physics. The wave function evolves according to the Schrödinger equation always, and whatever we experience as definite outcomes must be understood within one of the interpretation frameworks, many worlds, relational cubism, or another without any physical collapse mechanism. The connection between quantum mechanics and consciousness has been raised periodically since the early days of the theory, most prominently by John von Neumann and then by Eugene Wigner. The argument runs as follows. The Schrödinger equation governs the evolution of quantum systems, and measurement devices are quantum systems, and brains are quantum systems. So the Schrödinger equation should apply to the entire measurement chain, including the brain of the observer. But the Schrödinger equation does not produce definite outcomes. It evolves superpositions into larger superpositions. If the observer's brain is in a superposition, who is having the definite experience? Wigner proposed that the consciousness of the observer caused the collapse. When a conscious observer became entangled with the measured system, consciousness introduced a non-quantum element into the dynamics that collapsed the wave function. This is called the consciousness causes collapse interpretation, and it is not widely accepted among physicists today. The most fundamental objection is that it introduces a privileged role for consciousness in physics without providing any mechanism or account of what consciousness is or how it interacts with quantum systems. The Wigner's friend thought experiment, which Wigner introduced in 1961 to illustrate his point, has become increasingly central to discussions of quantum foundations as experimental technology has improved. In the thought experiment, a physicist called Wigner is outside a sealed laboratory. Inside the laboratory is Wigner's friend, who performs a quantum measurement. From the friend's perspective, the measurement has a definite outcome. From Wigner's perspective, the friend and the measured system have evolved together according to the Schrödinger equation, and the friend is in a superposition of having seen two different outcomes. This creates a potential contradiction. The friend has a definite fact about the measurement outcome, but Wigner's quantum description assigns no definite fact to the friend. The contradiction can be sharpened by having Wigner perform a measurement on the entire laboratory, a measurement that could detect whether the laboratory as a whole is in a superposition, and then comparing notes with the friend. Recent work by Václav Bruckner and others has derived no-go theorems analogous to Bell's theorem for the Wigner's friend scenario, under specific assumptions about the consistency of facts between observers. It can be shown that quantum mechanics is incompatible with assuming that all observers share consistent facts about the world. At least one of several natural assumptions must be abandoned: the universality of quantum mechanics, the existence of objective facts independent of observers, or some form of locality or consistency condition. Experiments probing these questions using photonic systems, in which one laboratory is replaced by a quantum optical system that simulates the friend's measurement, have been performed in recent years and have confirmed quantum mechanical predictions while violating the classical assumptions needed for consistent observer-independent facts. These experiments do not resolve the interpretation question. They cannot, because all mainstream interpretations agree on the quantum mechanical predictions. but they demonstrate that the Wigner's friend paradox is not a thought experiment that can be dismissed on grounds of technical impossibility. It is physically realizable, at least in simplified form, and the predictions of quantum mechanics in that scenario are experimentally testable. The landscape of open questions in quantum physics is therefore wide and deep. At the technological frontier, the challenge is building quantum devices with sufficient fidelity, scale, and coherence time to achieve fault-tolerant quantum computation and practical quantum communication networks. At the experimental frontier, the challenge is testing the boundaries of quantum mechanics in regimes where modifications might be detectable, large mass superpositions, Wigner's friends scenarios, Bell tests with new loophole closure requirements. At the theoretical frontier, the challenges include understanding the emergence of spacetime from quantum entanglement, resolving the black hole information paradox, and developing a complete theory of quantum gravity. Underlying all of these is the foundational challenge that has been present since the beginning. Understanding what quantum mechanics says about the nature of reality, whether properties are defined before measurement, whether the wave function represents reality or knowledge, whether the universe branches into many worlds at each measurement, or whether collapses occur physically, or whether facts are only defined relative to observers, or whether the question itself is malformed. 100 years of quantum mechanics have not answered this question. They have sharpened it, constrained the space of possible answers, and demonstrated that the classical picture of a definite, objective, observer-independent world is not supported by experimental evidence, but the replacement picture, what the world actually is, if not a collection of objects with definite properties, remains to be fully specified. This is not a failure. The history of science contains many examples of long periods in which a theory was used productively without a full conceptual understanding of its foundations. Newtonian mechanics was used for centuries before anyone understood the nature of force in a philosophically satisfactory way. Thermodynamics was practically successful for decades before its statistical, mechanical underpinning was developed. The operational success of quantum mechanics, its extraordinary predictive accuracy, its technological applications, its explanatory reach, does not require that the foundation's question be settled first. But the foundation's question is not merely philosophical. The development of quantum gravity and the attempt to understand what the universe is fundamentally made of requires a clear understanding of what quantum mechanics is saying about reality at every level. Building a quantum theory of spacetime requires knowing whether spacetime is emergent or fundamental, whether information is conserved, whether the wave function of the universe is a meaningful concept. These are foundational questions, and progress on them will require theoretical breakthroughs, not just more experimental data. The current moment in quantum physics is defined by exactly this combination: extraordinary practical success, powerful new experimental capabilities, and deep unresolved foundational questions. The gap between what quantum mechanics lets us do and what we understand about why it works is not closing. In some ways, as the experiments become more precise and the questions more sharply posed, the gap is growing. The more we test quantum mechanics, the more precisely we know it is correct. And the more precisely we know it is correct, the more pressing the question of what, exactly, we have learned about the nature of reality. That question has no quick answer, but it is the right question, the one that sits at the junction of physics, philosophy, and the human attempt to understand the world at its most fundamental level. It has occupied the greatest scientific minds of the past century. It will occupy the greatest scientific minds of the next century, and it will be answered, eventually, by a combination of experiment, mathematics, and conceptual revision that we cannot yet fully anticipate. The universe did not have to be this way. There is no a priori reason why reality at the smallest scales had to be, or why properties had to be undefined before measurement, or why entanglement had to produce correlations that exceed local limits. These are discovered features of the world, not inevitable consequences of any prior principle. The fact that they hold up under every test performed with increasing precision over 100 years suggests not that they are a temporary approximation to something deeper, but that they are genuine features of reality, facts about the world that any future theory must accommodate. Whatever that future theory turns out to be, it will inherit the quantum mechanical structure of the present one. It will require superposition. It will require entanglement. It will require complex amplitudes. It will require the violation of Bell inequalities. These are not negotiable because the experiments have established them. The future theory may explain why these features exist, or may reveal a deeper structure from which they emerge, but it will not eliminate them. We live in a universe that, at its most fundamental level, does not behave the way we perceive it to at the scale of everyday life. The definiteness of ordinary objects is not a reflection of underlying definiteness. It is a large-scale statistical approximation to a fundamentally indefinite quantum reality. The solid table, the reliable clock, the predictable orbit of the moon. These are emergent phenomena, arising from the collective behavior of quantum systems in regimes of strong decoherence, not evidence for a classical foundation. Beneath the quantum formalism, understanding this does not change how the table feels or how reliably the clock runs. The classical world remains a useful description at the scales where it is accurate, but understanding it does change the picture of what the world is. And that picture, though incomplete, is the most accurate picture of reality that science has yet produced. If you want to follow this conversation as it continues, as the experiments push into new regimes, as the theoretical frameworks mature, and as the foundational questions either resolve or deepen, that conversation is ongoing and accelerating. The next decade will bring more quantum computers, more precise Bell tests, more sophisticated Wigner's-Friend experiments, and potentially the first experimental constraints on theories of quantum gravity. Each of these will add detail and precision to a picture that is already far stranger and more accurate than anything classical intuition could have predicted. The picture is not finished. The question of what reality is at the quantum level remains open, but it is being asked more precisely and answered more carefully than at any point in the history of physics. And it is worth following. There is one further thread worth pulling: the role of symmetry in quantum mechanics, and how it connects the abstract mathematical structure of the theory to the specific physical world we observe. Modern physics is built on symmetry principles. A symmetry, in the technical sense, is a transformation that leaves the laws of physics unchanged. The laws of physics are the same at every location in space. Spatial translation, symmetry, and this, by Noether's theorem, implies the conservation of momentum. The laws of physics are the same at every moment in time. Temporal translation, symmetry, implying conservation of energy. The laws of physics are the same, regardless of the direction of measurement. Rotational symmetry, implying conservation of angular momentum. These conservation laws are not independent discoveries. They are consequences of the symmetries of the laws of physics, derived from a single, elegant theorem proved by Emmy Noether in 1915. The connection between symmetry and conservation is one of the deepest structural features of physics, and it extends directly into the quantum mechanical framework. In quantum mechanics, physical observables, quantities like energy, momentum, and angular momentum, are represented by Hermitian operators acting on the quantum state space. The symmetries of a physical system correspond to unitary operators that commute with the Hamiltonian. The operator representing the total energy. When a symmetry is present, the associated conserved quantity has a definite value in any energy eigenstate, and that value does not change over time. The standard model of particle physics, which is the most precisely tested theory of the fundamental interactions, is built entirely on symmetry principles. The electromagnetic force arises from a symmetry called U1 gauge symmetry. The freedom to independently multiply the quantum wave function at every point in space by a complex phase factor. The weak nuclear force arises from a symmetry called SU2 gauge symmetry. The strong nuclear force arises from a symmetry called SU3 gauge symmetry. These are internal symmetries. They do not correspond to symmetries of spacetime, but to symmetries of the fields themselves. The gauge principle, the requirement that physical laws be under local gauge transformations, essentially determines the form of the interactions between particles, starting from the symmetry and requiring local invariance. You are forced to introduce gauge bosons, force-carrying particles, whose properties are fixed by the symmetry group. The photon, the carrier of the electromagnetic force, is the gauge boson of U1 symmetry. The W and Z bosons of the weak force are the gauge bosons of the SU2 symmetry. The gluons of the strong force are the gauge bosons of SU3. This is remarkable. The specific forces that exist in nature, not their strengths, but their form, the way particles interact, the nature of the force carriers, are determined by symmetry requirements. The structure of the physical world, at the level of fundamental particles and their interactions, is encoded in the symmetry properties of quantum fields. Physics, at this level, is geometry, not the geometry of ordinary space, but the abstract geometry of field configuration, spaces under group actions. The one interaction not yet incorporated into this framework on equal footing is gravity. General relativity can be formulated as a gauge theory of sorts, with local Lorentz symmetry and diffeomorphism invariance, playing roles analogous to the internal gauge symmetries of the standard model. But the technical challenges of quantizing gravity, of building a quantum theory whose classical limit is general relativity, have not been fully overcome in the same way that the other interactions were brought into the quantum framework in the second half of the 20th century. Understanding why gravity is so much harder to quantize than the other forces is itself a deep question. Part of the answer is that gravity is both a force and the geometry of spacetime itself, and quantizing geometry requires a different approach than quantizing fields that live on a fixed geometric background. Part of the answer is that general relativity is non-renormalizable as a perturbative quantum field theory, meaning that attempts to calculate quantum gravitational corrections generate infinitely many divergent terms that cannot be absorbed into a finite number of physical parameters. String theory addresses the problem by replacing point particles with extended strings, which introduces a natural short-distance cutoff at the string scale and eliminates the ultraviolet divergences. Loop quantum gravity addresses it differently, by quantizing the geometric variables of general relativity directly rather than treating geometry as a background. Neither approach has yet produced a complete, experimentally confirmed theory. Both continue to generate mathematical insights that connect to the broader program of understanding how quantum mechanics and gravity coexist. The program that will eventually test quantum gravity faces an extraordinary challenge of scale. The Planck length, the scale at which quantum gravitational effects are expected to become significant, is approximately 1.6 times 10 to the minus 35 meters. The smallest scales directly probed by current particle accelerators, like the Large Hadron Collider at CERN, are approximately 10 to the minus 19 meters. The gap between the experimentally accessible scale and the Planck scale is 16 orders of magnitude. Closing that gap with direct particle physics experiments is not feasible with any technology that can currently be imagined, but indirect tests may be possible. Certain quantum gravity scenarios predict specific modifications to the dispersion relation of photons. A slight energy dependence on the speed of light at very high photon energies. High-energy gamma-ray photons from distant astrophysical sources, like gamma-ray bursts, can be used to test this. If high-energy photons travel very slightly faster or slower than low-energy photons, photons emitted simultaneously but with very different energies would arrive at slightly different times after traveling across cosmological distances. The Fermi Gamma-ray Space Telescope has performed these tests and has placed constraints on quantum gravity models that modify the photon dispersion relation. So far, no violation has been detected, placing strong lower bounds on the energy scale at which any dispersion modification can occur. Gravitational wave astronomy, opened by the first detection of gravitational waves by the LIGO collaboration in 2015, provides another potential window into quantum gravity. Gravitational waves are ripples in the fabric of space-time itself, and their precise waveform encodes information about the geometry of space-time in extreme conditions. Near merging black holes and neutron stars, as detector sensitivity improves, gravitational wave observations may eventually test the quantum structure of space-time near the Planck scale, particularly in the context of black hole mergers where space-time curvature becomes extreme. The intersection of quantum mechanics, information theory, and gravity is where the most active theoretical work in fundamental physics is currently concentrated. The insights developed through the study of holography, black hole thermodynamics, and quantum error correction have already reshaped how physicists think about space-time, information, and the nature of quantum systems. The next decade will see these ideas tested more sharply, refined mathematically, and connected to experimental programs in quantum computing and quantum gravity that are currently being developed. What quantum mechanics has taught us, over a century of increasingly precise tests, is that the structure of reality is not what it looks like from the outside. The familiar world of solid objects, definite properties, and predictable behavior is a high-level approximation, accurate and useful at the scales of ordinary life, but not a reflection of what is actually happening at the level where the fundamental laws operate. At that level, properties are defined by interactions, outcomes are determined by measurement, correlations exceed what any local classical mechanism can produce, and the background of space and time may itself be an emergent structure arising from a deeper quantum reality. That picture is strange. It is also, by every experimental measure available, correct.